Hi everyone, welcome again to another edition of the Focus on Geothermal webinar series, a partnership between ThinkJ Energy and Enerchange. And once again, I'm Carlo Cariaga from ThinkJ Energy. And today we have the pleasure of hosting Dr. Bruce Mountain, Senior Geochemist and Lead Scientist of the Experimental Geochemistry Lab of GNS Science in Wairakei, New Zealand. The webinar today will discuss the cutting-edge research being done by the Experimental Geochemistry Lab on supercritical conditions, high-fidelity reservoir simulations, and solutions for managing scaling, corrosion, and reservoir injection in geothermal systems. Today, we will learn about how the laboratory replicates real-world geothermal conditions and provides critical insights into fluid-rock interaction, material durability, and the potential for mineral extraction. We will also learn how the work ultimately reduces operational risks, lower costs, and enhances developments worldwide. Our guest today is Dr. Bruce Mountain, who has over 25 years of experience in geothermal geochemistry. He specializes in rock interaction, scaling, and corrosion mitigation, and reservoir management. His expertise supports both commercial and research partners in optimizing geothermal energy systems, ensuring long-term sustainability and efficiency. So before we start, for those in the audience, you may send in your questions via the questions tabs, which you can find somewhere in the webinar interface. Before anyone asks, this webinar will be recorded and it will be uploaded on our YouTube channel in about a week. So it's my pleasure to welcome Bruce. Bruce, the floor is yours.
Thank you very much, Carlo. I'd just like to welcome everybody to this webinar. Thank you for attending. Geothermal energy, of course, holds enormous promise as a sustainable and low emission energy source. But as many of you know, the use of geothermal energy is not without its challenges. And particularly in the geochemical area, things like scaling and corrosion and reservoir management are important things we need to consider when we're making geothermal development. So today I'm going to be talking about the use of experimental geochemistry and specifically high temperature pressure flow through experiments that can better help us to understand and manage these challenges. So what is experimental geochemistry? Well, experimental geochemistry is the study of how rocks, minerals, metals, and fluids interact, but under controlled laboratory conditions. We want to simulate environments where pressure and temperature preclude the direct observation because it's simply too extreme for us to go there, or it's difficult, expensive, or outright impossible. We can use experimental geochemistry to investigate geochemical processes to understand, predict, mitigate, or prevent current or future challenges in geothermal development that impact sustainability and efficiency of geothermal energy production. So what are some of the geochemical challenges? Well, first we can look at water rock interactions in the production zone. So that's mainly water rock interaction that's occurring already. So things that may be important to the production of energy based on the chemistry of the existing fluids. We have mineral scaling and production wells, mineral scaling and corrosion in plant infrastructure, the determination of optimal dosing pH in plant, the emission of greenhouse gases, and mineral scaling and corrosion in reinjection lines, and mineral scaling and injectivity loss during reinjection. So these are all scenarios where we can have problems, and experimental geochemistry, lab-based experiments, will help us to predict, mitigate, or prevent these problems. So just some history. The Experimental Geochemistry Lab at GNS Science was established in 2010 with the purchase of our first core test continuous flow-through system. And this system has the capability of going up to 400 degrees and 500 bars, allows a flow rate of 0.06 to 900 mils per hour. It has 2 titanium pressure vessels, and it it's quite resistive to corrosion. So this allows us to simulate water rock interaction with aggressive fluids. And in 2013, we bought a second core test system based on the successful acquisition of several research and commercial contracts. So one of the first things we worked on was brine reinjection simulations. So at a geothermal plant, when they're reinjecting geothermal brine, the brine is often not in equilibrium with the rock. So what results is mineral fluid rock interactions in the reinjection reservoir, and this can cause problems. So we had to develop a testing scenario whereby we could reproduce the reinjection of a brine. So this is just a simple diagram of the core test system, which consists of a double piston metering pump, a separator, which has a sliding disc inside that separates the distilled water from the pump from the actual geothermal brine, which is the red arrows. This distilled water is the blue arrow here. And you can see it goes through a preheater vessel, we call it, and this preheater vessel is empty, and this depolymerizes silica. So you know the problem with dealing with geothermal brines from a power station is that the silica polymerizes when the brine cools. And so we can't directly pump geothermal brine from a power station into a hot rock in the laboratory because the silica is already polymerized. So we had to develop a method whereby we could reconstitute the brine back into its composition when it was in the plant, whereby it never actually cools to room temperature before it's reinjected. So this is what the preheater vessel does. The preheater vessel actually depolymerizes the silica, typically heated to 250 degrees, and it dissolves the silica polymers back into monomeric silica. So during a reinjection simulation, we take rock. So we actually take rock from the actual location. We ask whoever the client is to provide us with a representative rock from where they think the reinjection horizons are. And we crush it and we sieve it to a certain size fraction and we clean it to get rid of fine material, which reacts differently. We also, as best we can, get a brine from the actual location if it's available. If it's a brine that's not available, we can reproduce the brine as best we can from chemistry analyses. So we take the rock and the brine, we put the rock in the pressure vessel, and we flow the brine through the preheater and then the pressure vessel, the reactor, which contains the rock. And that can be at the reinjection temperature, which is typically 80 degrees to 150 degrees. So this is typically done over 28 days. We keep a standard protocol so that we can compare experiments. So done over 28 days at whatever reinjection temperature at a flow rate of 5 mils per hour, which gives us enough sample every day to do our chemical analyses. So what you see in the middle here is when we take the rock out, sequentially from the bottom to the top, and we divide it into 10 portions. So these positions, you see number 1 to 10, represent the position in the pressure vessel. So 1 is the bottom of the pressure vessel, and that's where the brine enters. And then it passes up through these different layers and exits out the top at position 10. So 1 is where the brine enters, and 10 is where the brine exits. You divide the brine up into 10 portions, and then we do really in-depth sophisticated SEM measurements on the surfaces to determine the surface composition, the average surface composition at each position. And so on the right here you see an example of the SEM EDS results. So the positions are the same as in the SEM photos. And this plots alumina and silica concentration on the surface of the grains. The dashed lines represent the average unreacted rock composition. So the blue is silica, the red is alumina. And what you can see there is very strong silica scaling, and you can see it in the SEM photos by the spherulitic sort of rounded surfaces, and then see at position 6 they disappear. And from 6 to 10 there isn't any. And you see that it's reflected in the surface chemistry. We've got over 95% silica on the surface and much less aluminium compared to the unreacted rock. But once we pass position 5, the scaling stops, and this composition of the surfaces is very similar to the unreacted rock. So in this example, what we're seeing is very rapid silica scaling that stops very rapidly. So there's something going on at this position that stop the silica from scaling, probably the loss of the reduction in silica concentration. Another important thing that we can simulate is corrosion testing. Our current capability is up to 600 degrees, 500 bars. We can do extremely acid pH. We've done down to pHs of 3 and up to 10,000 parts per million chloride. We can do up to 600 degrees. This also required the development of a new experimental method, because standard corrosion testing is either done in the field, where you put coupons into existing lines and remove them, or it's done in a laboratory, typically by looking at weight loss of the coupon and then some SEM examination. We've had, because of the extreme conditions of these experiments, we've developed a different approach whereby we put the coupon, which consists of a bullet, we call it, which is 8 millimeters in diameter and 13 millimeters in length, and actually placed inside the titanium pressure vessel, surrounded by zirconium oxide ceramic. That prevents the bullet from touching the walls of the titanium pressure vessel, because there could be galvanic corrosion. Now, in this case, because we're not looking at silica scaling, we only use one pressure vessel, and we pass the fluid through at whatever rate we think is the best for that corrosion test, and we measure the actual concentration of metals in the fluid coming out. So particularly iron, which is most indicative of corrosion. And so we can actually get a much more detailed and sophisticated measure of the corrosion rate. If you're doing weight measurements, you can only get down to the sort of 5th decimal place of weight change. And then you have the problem of oxides forming, which increase the weight, sulfides forming, which increase the weight. So what weight changes tell you, it's a very rough estimate of corrosion rate. Here we can actually tell you how much iron has been lost to the micromole from the sample. So it gives a much more accurate measure of the corrosion rate of the sample. And here you can see some examples of corrosion of carbon steel with a carbonate H2S solution. And these euhedral grains here are siderite crystals, and these grains here are pyrrhotite crystals. And this is then the one on the top left here is the unreacted sample. This is the one on the right is the reacted sample. And so we're able to actually determine the actual mineralogy of the precipitates as well. The other thing we have addressed and developed new techniques for was looking at the optimum dosing rate. Many will be aware that silica polymerizes when it comes out of solution. When it's coming out of the ground, silica is present as monomeric silica. So this molecule here, down here. And then as the water cools and it passes the temperature passes below the saturation of amorphous silica, the silica starts to polymerize. So it forms dimers, trimers, tetramers, and eventually it forms colloids, which have millions of silica tetrahedra in them. The presence of these polymers and monomeric silica together in the plant causes the silica scaling, which is a serious problem if it's not dealt with. Now, the common everyday way of mitigating silica scaling in plant is to acid dose, which is a very effective technique, typically with sulfuric acid, giving a pH between 4.5 and typically 5.5, and that is very effective in the plant for mitigating silica scaling. However, every plant is different, every brine is different. The question is, what is the optimum dosing pH for the plant? And this is an important question because if your plant isn't constructed yet, you can't test it in the plant. So you have to determine ahead of time what dosing equipment you require for your plant. So it's nice to know what the optimum dosing pH is before you actually do the engineering design. Why is it important to get the optimum dosing pH? Is because if you're going too low, you're using excess sulfuric acid, which costs money, but also corrosion of the infrastructure is a serious problem. But if the pH is not low enough, then you have the potential of silica polymerization occurring in the plant or in the reinjection lines, which is an expensive problem to solve. So you want to get that sweet spot of the pH whereby the silica doesn't polymerize for a long enough period of time that is able to get back down the well. So if you don't mitigate the problem, you end up with this, which is silica scale. So the standard method for determining optimum dosing pH is by either a pilot plant, a field test plant, or doing field measurements. The drawbacks of this is that it requires a discharging well because you need fresh brine from the ground. It requires multiple personnel, requires the transport of sophisticated equipment like spectrophotometers. It's not ideal in locations with harsh climates. It requires mobilization of equipment and personnel, particularly if it's overseas and you don't have the equipment on site. It necessitates involved health and safety protocols for doing field work in a steam field. And clearly all this becomes time intensive. So the field measurement of optimum dosing pH is expensive, and it's difficult to reproduce results in the field because of all these factors involved. So we've actually addressed this issue by developing a technique using our hydrothermal equipment to do silica polymerization testing and optimum dosing pH determinations in the laboratory. So this has been set up by us, developed over the last several years. And now we are able to do silica polymerization testing in the laboratory. Now the three steps involved are the resuspension, because typically when brines come from an area with a very high salinity, the silica is flocculated by the time we receive it. So we actually get a silica flock in the bottom of the sample containers. So first step in there is resuspending the sample, and we have ways of doing that. Then we have to depolymerize the sample, which is done through use of the flow-through equipment. So we actually just run the brine through the flow-through at 300 degrees, and it redissolves the silica. And then we take that brine, and it's preserved at low pH. We take it to the laboratory benchtop, and we do polymerization testing by adjusting the pH. We can also do something that cannot be done in the field, which is we can do silica polymerization testing at temperatures above 100 degrees. So we actually have stirred pressure vessels whereby the brine is heated up past amorphous silica saturation to depolymerize the silica, and then it's cooled down to the reinjection or the dorching temperature in the same pressure vessel, and then we can actually sample over time the brine and measure the polymerization rate at temperatures above 100 degrees, which is something you cannot do in the field. So this is an example of a series of silica polymerization tests that were done on a real brine, a very high salinity brine. The brine was resuspended and depolymerized, and then these tests were done. And you can see this is a graph of the normalized concentration versus the time in minutes. So 880 is 3 hours, which is a typical time for a polymerization test. You want to get the brine out of the power station, down the reinjection line, and down into the ground before silica start polymerizing. So you can see at pH 7, which is the blue line here, we have polymerization. The induction time is less than 5 minutes, and it starts to polymerize. We can see that as we adjust the pH upwards, 6.5, 6, 5, and then below 5, there's almost no polymerization of the brine. So we can use these results to say at this temperature, the optimum dosing pH is somewhere below 5. And we probably could make it even more sophisticated by doing multiple tests. And they're very reproducible. So CO2 reinjection is another. So just to summarize, that was a technique that we developed to do silica polymerization testing in the laboratory. So we don't have to worry about field health and safety issues, shipping things overseas, long logistic trains, travel, all that kind of stuff can be avoided. So we estimate the cost of doing that is about 1/10 of what it costs to do it in the field. So, and so that means that we can do it on brines that are old. We did a polymerization test of a brine that was a year old. I was sitting under someone's desk, and it worked fine. So another question that comes up more recently is the reinjection of non-condensable gases, and it's gaining more and more importance in geothermal energy, particularly in New Zealand, because we have a carbon tax. And so geothermal energy production is not carbon emission free. So the only way to make geothermal carbon emission free is by reinjecting the non-condensable gases, particularly CO2 and methane. This will support sustainability and reduce atmospheric emissions from geothermal power stations. But there seems to be a slight out of sight, out of mind approach to this right now, whereby you just put the CO2 back in the ground and it's gone, magic. But the problem is that these brines have been boiled, acid dosed, had anti-scalant or anti-corrosion compounds added, cooled, NCG re-added back to them. You're putting that back into the ground and you're putting it into rocks, and rocks are not made of titanium. Rocks will react with these brines. So re-injecting NCG may not be problematic. Sorry. The laboratory simulation can help assess these reactions due to perhaps permeability increases due to mineral dissolution, but also permeability decreases due to mineral precipitation. So the experimental simulations aim to predict any potential changes in reservoir injectivity due to NCG reinjection. So the setup would be similar to the brine reinjection, but this time we're adding carbon dioxide to the brine. So logistically, it's not that much different than just a simple brine reinjection. So here's an example. This is at Wairakei. This is Wairakei from New Zealand, which is a typical bracement rock for a New Zealand geothermal system. And this is Wairakei that's been reacted with brine from a New Zealand power station. So this is real rock with real brine. It had 850 parts per million of silica and 4.5 pH. It was dosed with sulfuric acid. You can see this has been reacted for 28 days, 5 mils per hour at 150 degrees. So there would have been about 2 liters of water to go through over that month. And you can see that there is some silica scaling on the surface. So there's some spherulitic material. By the way, these photos are all at the same scale. The top and bottom photos are at the same scale. So you can see there's some spherulitic silica scale forming. And then when we add calcite to the rock, so we've actually added 2.5 weight percent of calcite to the same rock. So everything else is the same. And you can see there's dramatic silica scaling. And there's a loss of considerable amounts of silica. And the silica scale is quite thick when you compare it to the experiment without calcite. So what's happening is the reinjection brine, which is at pH 4.5, is going into the formation, and there's calcite if there's calcite in the formation, that calcite reacts very rapidly. And what it does is it neutralizes the brine, and the pH of the brine will actually go up to 7.8 or even 8. And as soon as that happens, of course, all your acid inhibition of silica polymerization and scaling is gone, and you're actually precipitating out dramatically a large quantity of silica quite rapidly because of the high pH. So what's this got to do with CO2 reinjection? Well, the photos at the top here are the exact same photos as before when we had brine with calcite. So we can see again, there's quite a thick silica, but then we did the exact same thing. So this is brine with calcite, Wairakei with calcite, but then we added 0.2% carbon dioxide. So basically we're re-injecting CO2 now, and there's no silica scaling. So CO2 is actually a silica anti-scalant. How does that work? It's because CO2 is a pH buffer. So when you add CO2 to the brine, you're forming carbonic acid. So every time an H plus is consumed by the calcite, the carbonic acid molecule dissociates to form H plus and bicarbonate. So it's acting as a pH buffer. And so instead of the pH going from 4.5 to 8, the pH goes from 4.5 to 5.5. And the CO2, the carbonic acid, keeps the pH buffered. And so you have no polymerization of silica. So the fluid can pass the formation, even though there's calcite present, without the pH actually being neutralized. And it's a win-win-win because you're getting rid of the CO2, you're stopping the silica scaling, but it also dissolves the calcite out faster than the brine without CO2. Because of the acidity, the calcite in the rock actually dissolves faster. And so it's basically acting as a cleaning agent of the formation. It actually dissolves the calcite out of the formation, which is the culprit that's causing your silica polymerization. So we look at the chemistry. So this is the same type of diagram as I showed you previously. So if we look at the brine with Wairakei calcite, we can see when the fluid enters, we've got higher silica at all positions, And it's all greater than the original rock content, which is this blue line. This blue line is the average rock surface composition. The blue band is plus or minus 1 standard deviation of that composition. And you can see the surface composition of silica. They're all consistently higher than the unreacted rock, and the aluminium concentrations are lower, which means the silica is covering the rock minerals. And you can see the spherulitic precipitates on this rock. What is interesting about this experiment, this is a different experiment than the other one, is that the silica is thicker at the top of the pressure vessel. So remember, the fluid's entering here, but it's exiting here. But the actual silica is actually thicker at the top of the pressure vessel this time than at the bottom, as I showed you previously. This points out the importance of the difference between different fields, different rocks, different brines. I've done many of these experiments, and I tell you, almost every one of them is different. This is something to do with the kinetics of the silica precipitation. It's actually being delayed, and then as chemistry changes, as the fluid moves up the pressure vessel, it triggers faster silica precipitation. This is the exact same rock and brine, but this time, and calcite added, but this time we've added 2,000 ppm CO2, and there's no silica scaling. You can see that the average and mean, the green is the mean, the red is the average surface composition of the reactive material. The bars are the 1 standard deviation. And you can see that pretty much they all lie slightly above the average, but generally compared to this one here, there's no silica scaling, and the aluminium is indistinguishable from the unreacted rock. And then when you look at the SEM images, you don't see these spherulitic precipitates. So one of the other things we're interested here in New Zealand is supercritical. And supercritical systems are deeper and hotter and contain much higher heat content. So the experimental geochemistry lab has also been involved in doing work simulations involving supercritical geothermal. So in 2019, we purchased a PAR high temperature flow simulator, which is the only one in the world. It's capable of going up to 700 degrees and 290 bars, continuous flow. And we've used it to look, the applications for this are to look at supercritical fluid rock interactions, mineral solubilities at supercritical conditions, corrosion testing, and looking at tracers, because what tracer are we going to use at 400 degrees, 450 degrees? This is just a simple schematic. Has used HPLC pump with a Brock, we can use blocks or we can use crushed grains. Pressure vessel heated to whatever temperature. Back pressure regulator is this, and its back pressure regulator is powered by compressed nitrogen. So this is an example of some of the work that we've done. This is published in 2023 in the Journal of Supercritical Fluids. This is the solubility of quartz from 375 to 600 degrees and 270 bars. And you can see these beautiful solubility data along the isotherms. Each dot represents 20 measurements, and they're separated by 5 bars. So we're able to distinguish the change in solubility at 5-bar increments at these extreme temperatures. And we can see as we approach the critical point, so we're getting close to the critical point at 400, the solubilities start to go up, and at the critical point, the solubilities go up almost exponentially to infinity. And this is results for anhydrite, because that's another mineral that probably really important when looking at scaling. This is published in Geochemica Cosmochemica Acta last year. This is from 380 to 625 and 220 to 270 bar. Note the concentrations. These are part per billion concentrations. Very, very difficult. You can see these data here are all compressed down into this area here in this diagram. So you see the maximum solubility we got was at 380 degrees, and that was about 800 ppb. So this represents about 800 parts per billion. So you can see the solubility of anhydrite is pretty darn low under these conditions. So I wouldn't expect much to dissolve, but I wouldn't expect much to be able to be carried in solution either. It's interesting because when we go up to higher temperatures, the solubilities actually start to go up. It's counterintuitive because we can see as the density of the water goes up here, the solubility goes up. But if we look at detail at the lower end of the data, you can see that as the density of water is decreasing, the solubility is actually increasing. And this is probably because we're now forming a volatile calcium sulfate phase. It's not actually as an ion anymore. It's actually calcium sulfate gas at these very low pressures. Also, water-rock interaction is very interesting at these conditions. We can see here on the left, we have the unreacted rock, and in the middle, we have the Wairakei. This is Wairakei, by the way. Wairakei reacted with distilled water at 400 degrees, and we have a covering of actinolite. Note the density is 0.65 grams per centimeter at this condition. And then we have the same at 500 degrees, and the density of water at this condition is 0.35 grams. So you can see the water density dropping. And at 500 degrees, the rock is covered with cristobalite. And this is very interesting because where we see similar types of precipitates are in volcanic fumaroles. So you think of a volcanic fumarole being very hot fluid, mostly water, but it's precipitating silica directly from that fluid. Well, it's analogous to what's going on in these experiments at very high temperature. If we put geothermal brine, so this is real geothermal brine from a power station in New Zealand. Again, this is the unreacted on the left. In the center, we have Wairakei reacted with brine this time at 400, and we get a albite precipitate, mostly albite precipitating the surface. And very interesting, at 500 degrees, 250 bars, we have quartz. So these grains here are actually doubly terminated quartz crystals that have grown on the rock. And these fine needles and these strange platelets, I think, are amphiboles. We're not entirely sure. They're very strange minerals, but I'm pretty sure that I'm pretty sure they're amphiboles. When we add carbon dioxide, some interesting thing happens. This again is the unreacted rock. This is exactly the same as the previous experiment at 400, but there's CO2 now, 0.2%, I believe, CO2. And you can see that this is a rock block. You can see the scale here. That's 0.1 millimeters. This block of rock has been severely corroded. This is an albite crystal classed in the Wairakei, and you can see it's been severely corroded. There's also a lot of secondary phases. These cubes are anhydrite. You can see again at 500 degrees, we've got very nice anhydrite crystals growing and a background of albite. And these needles are again, I think, an amphibole of some kind, possibly actinolite. What's interesting is the only difference between this experiment and the previous one is the CO2. So why there's no quartz forming in this experiment. So what we think is happening is the pH is so low with the CO2 added that it's aggressively attacking the rock and it's releasing a lot of calcium, and that's forming the anhydrite. But it's also releasing a lot of aluminium and silica from the rock surface, and it's being reprecipitated so rapidly that quartz never saturates. And so quartz cannot grow. And it's because the lower pH, we suspect, at 500 degrees. This is also shows an EDS map of the surface of the rock. And you can see that on the left is the unreacted rock. The red is silica, the green is alumina, and the blue is sodium. And you can see the reacted rock scanning the exact same region. These black holes are shadows. They're actually, the silica is gone. And there's quite a bit of sodium also removed from the surface too. So we can see that this supercritical fluid, this is distilled water, by the way, the supercritical fluid, distilled water, is actually removing quite a bit of material from the surface. So the latest development in our lab is the acquisition of a new flow-through equipment. We call it the GPS, the Geothermal Process Simulator. It was built by Vinci Technologies in France. And it's a hydrothermal flow simulator, and it's globally unique. There's only one of a kind. It's capable of going to 600 degrees, and it has a double autoclave, double pump system, which allows the introduction of a second fluid between the reactor and the preheater. And so you can see this here. This is the two ovens. These are the separators that contain the two fluids. That's the back pressure regulator. And, oops, sorry. And this animation shows you the flow path. So you can see the blue fluid is coming out of the first separator. It's passing through the preheater. The second fluid is coming out of the second separator, and they mix together between the two pressure vessels. Then they go through the second pressure vessel, the reactor, and they come down and they're collected in the syringe. So this setup allows us to pass a fluid, mix a fluid in between the two pressure vessels. And if you remember correctly, the first one is the preheater for reinjection simulations, and that depolymerizes the silica. But if we want to test an anti-scalant compound, we don't want to have to heat that compound up to 250 degrees in the preheater. We want to put that in there without preheating. So that's why that's how we can put the second fluid can contain the anti-scalant and go up in between the two, and it's actually not heated. And then the two mixtures can go into the reactor where the rock is, and we can test anti-scalants, for example. The other thing we can do is we can change the pH over the experiment. In the older equipment, we have to put everything in the first separator, and of course it has to go through the preheater. And we could only put one pH in, otherwise we'd have to empty this out and refill it. Now we're able to put a acid or a base in this, and we actually dose the brine as it comes through and adjust the pH. So this is basically acting as an acid dosing simulator. And so we can look at silica polymerization rates by adjusting the pH over the experiment. So takeaway messages. So our lab can reproduce hydrothermal conditions in a controlled laboratory setting up to supercritical conditions and pressures. And this allows us to help study geothermal, geochemical challenges in geothermal energy production, including scaling issues, corrosion rates, thermodynamic properties, and testing additives. We have to develop, one of our missions is to develop new protocols to do things that people haven't done before. So often we come with the question, can you do this? And our response is, let's go away and think about it. Our team will go away and think about it, and we'll say, okay, we can do this by setting up the following protocol. And all the methods that I've talked to you about today were all developed in our lab. We have been very successful at marketing these things as a tool to help people predict or mitigate problems in geothermal energy production. So our research and our experimentation contribute to advancing geothermal energy in technology and its sustainability. But most of all, we want to do exciting science and to boldly go where no geochemist has gone before. Thank you very much.
All right. Thanks, Bruce. That was, I find it very interesting. It's like you're playing with a lot of these fancy, expensive toys in your lab, and I'm quite jealous with it.
It's a challenge, believe me.
Okay, then. So for everyone in the audience, you are free to ask questions. Just type in your questions in the questions tab, and we'll get to those as we go along. We have 20 minutes for the questions. Okay, so let's get started. I've heard that New Zealand geothermal power plants have already started with the practice of NCG reinjection. And so, how has your results in the lab scaled up or manifested in actual reinjection procedures? Like, have you observed? Has there been an observed increase in, say, injectivity of these wells?
Good question. They've only really started reinjecting just recently. So if you're looking at real world effects of CO2 reinjection, we don't know yet. However, I can guarantee you that if you have a power station where you're having loss of injectivity due to silica scaling near the annulus of the reinjection bores, this CO2 reinjection will stop it. I guarantee it. The silica will precipitate. Remember, the silica always precipitates or equilibrates eventually, but the drive is to get that silica away from the well. And as you get it away from the well, you've got more and more rock volume to deposit it in. So it's going to precipitate, but you don't want it precipitating within 50, 100 meters of the well. And that's where the problems start. So,
Sorry, go ahead.
In the laboratory, these things stop the scaling. Whether it's going to happen in the field, we need a year, 2 years, 5 years, 10 years down the road to see a change in ejectivity of a well. And Yeah, so we don't know, but I'm pretty confident that CO2 reinjection. Remember, we've done experiments with New Zealand power stations that have been contracted, right, by the producers, not as research projects. We've actually done a couple of sites, and it definitely prevents silica scaling in the experiments. So yeah, I'm pretty confident that it will help with injectivity losses. There's a drawback, of course. There's not a drawback. There's a potential drawback in that you might form anhydrite because you're increasing the calcite, the anhydrite, calcite solubility, because you're keeping the pH low. So it's dissolving more calcite, and it's also got a higher CO2. So there's a potential, not of calcite precipitation, the pH is far too low, but of anhydrite precipitation because it's an acidose brine. That may be a problem, but people ask me that, but I keep in mind the amount of anhydrite that you precipitate is tiny compared to the amount of silica. You know, you're talking hundreds of ppms of silica precipitating. Well, it may be only a few ppms of anhydrite, and it may be only when the fluid gets up to 300 degrees or something deep in the reservoir. But like it goes back to your question, we don't know what's going to happen unless we model it, which is needed. Like I said in my talk, there's sort of an out of sight, out of mind attitude. Oh, let's just put it down on the ground. Let's not worry about it. And I think that's a big mistake. So we do need, I think we need to do more experimentation and more modeling about what happens to that fluid as it goes deeper. Sorry, I'm talking too much. Yeah.
That's fine. Someone in the questions commented that this is also, I mean, CO2 injection is already being done in say outside of New Zealand. I believe in Germany,
Yeah.
also in, and I think they have been getting fairly good results. Do you know about those?
There's two things to remember: storage and sequestration. In Iceland, they want sequestration, and they can do it in Iceland because they've got basalt. And basalt is full of calcium, magnesium, and iron, which fixes the CO2. They know it's doing that. They've drilled wells and everything. It works great, fantastic. You can't do that in a silicic basement rock. Wairakei here in New Zealand, which is the dominant basement rock where you're going to be re-injecting, right? And then all the volcanoes are mostly rhyolites as well. There's very little 2+ cation to fix, and so you will not get any sequestration. It is only going to be a storage thing. So what you're doing is when you're re-injecting, you're hoping that the input from below, the magmatic input, is not really fast, really high, because you're putting that CO2 back in the ground and you're hoping that it's just going to be stored. So it's going to circulate. And I'm a proponent of actually putting more CO2 into the reservoir than you're actually taking out of it. So it's like topping it up like you would in your car. You put in the CO2, you try to keep it higher than what you're actually removing, and that actually keeps the formation clean of calcite. But again, that's a concept, and it's all based in geochemistry, not on modeling. But I think that actually putting more CO2 in the system could actually be beneficial. But going back to your question, you're not going to get sequestration in a basement rock that's highly silicious. That's the question.
Okay, we have we have a lot of questions coming in, and they're all on CO2 reinjection.
Okay.
Okay, so there's another question here. I think an excellent point. As you mentioned, CO2 reinjection reduces the pH of the brine, makes it more acidic. So is corrosion a concern here, or is it not that acidic?
Okay, this is an engineering problem. I'm not a power plant engineer. I'm a geochemist, so I work by reactions and what makes sense on paper. Corrosion is an issue because when you put CO2 back in, when you put NCG back into the brine, you reduce the pH. But you're also acidosing the plant in a lot of cases, in which case the pH is already 4.5. So when you add another 2,000 ppm of CO2, it goes to 4.3 or something like that. So it's because you're adding carbonic acid, so it's not really increasing the acidity much. That said, yeah, okay, maybe you're going to have corrosion in your reinjection lines, maybe. So what's the answer? You reinject at the reinjection well. You put the CO2 down the reinjection well with the brine at the wellhead. I don't know engineering. This thing called bubble blocks and stuff like that. Those are engineering problems that need to be solved. But your only other choice is to put it in the air, right? And in New Zealand, that costs you $70 a ton. So yeah, corrosion is an issue, but deal with it, right? It's an engineering problem.
Okay, then let's move on to the supercritical side of things.
Yeah.
We already, right now, there are a few projects that are dealing with very deep drilling, expecting supercritical temperature, supercritical conditions, rather. And one of the major challenges here is often material selection. So, casing material, probably the electronics as well for drilling. So, is it possible for your lab to test these sort of materials or equipment in supercritical conditions?
Yeah, well, I mean, basically the equipment itself is a test. Now, most of it's titanium, which is not very, it's very, very resistant. But yes, the answer to your question is yes. I mean, we've already done quite a bit of corrosion testing, up to 400 degrees. I think the temperature limit now, we have a client maybe wanting 450 degrees. Yeah, I mean, we can test anything. I've tested plastic, like peak plastic with seawater at 200 degrees. We can test any material, solid material, with brine at any condition, up to 600 degrees.
Okay, then, and then I guess that's something that's interesting for some of the projects that are going on right now. Can you make a comment on, say, the long-term implications of casing and also even surface equipment if you try to extract geothermal resources from a supercritical reservoir?
It's a difficult question because I really need the chemistry. What's the chemistry? If it's pH 2, you've got a problem. If it's pH 6, not so much. Scaling, I don't direct extraction of supercritical fluids. Scaling won't be a problem because silica concentrations are all really low and nothing else really gets carried in the brine. You'll have volatiles, you have CO2 and H2S, but you won't have a lot of dissolved solutes because things are not soluble in low density fluids. The problem is, of course, those fluids condense, and then who knows what happens. Perhaps you might want to look at some kind of heat exchanger type scenario where you're actually just extracting the heat rather than the fluid itself. I think there's a lot of engineering issues and drilling issues when it comes to supercritical development, but that's not for me to answer. I'm not an expert on those things.
Okay, then. One thing I found very interesting in your results is that you showed that solubility of, say, anhydrite is very low under supercritical conditions. So does that also imply that extracting these fluids has a very low risk of scaling?
Yeah, because you could. I didn't point out this. The silica solubilities are only on the order of 100 ppm as well. Quartz solubility. So if you have a supercritical fluid, there's basically nothing in it. It's going to have CO2 and H2S and methane and things like that. It's going to have volatiles, and it has silica in it by the fact that silica is a neutral molecule as well. So it's just floating around in there. But the other things, just when we do experiments and we measure you see those experiments, you see there's a lot of new minerals forming on the rock. In the fluid, there's almost nothing. So those reactions are occurring on the surface of the rock, and it's very interesting because they shouldn't be that soluble, right? And so we actually think there's a condensed water layer on the rock, that the actual reactions are occurring in this condensed water layer on the surface of the rock, but actually in the bulk fluid, there's nothing. So to answer your question, if you're taking that supercritical fluid directly, your main problem may be acidity due to CO2 and H2S rather than anything else.
Okay, now let's move on from maybe scaling to corrosion. As you mentioned, you might be
Yeah.
dealing with volatiles, but I mean this may be a little outside of the scope of your presentation, though. But I know that you've done a little bit of a lot of research on, say, magmatic gases, magmatic compounds. So, do you think that this is going to be a serious consideration when you're tapping into very hot reservoirs? Do you think that you're also tapping into more magmatic gases, say HCl,
you,
SO2?
you you've got to be careful. Here in New Zealand, at least, we're looking at supercritical systems that are not magmatic systems. The only thing that's coming from the magma is the heat and perhaps some volatiles. We're not talking about magmatic fluids. That's a whole different thing. You're talking about super high salinities, right? Very high pressures, like, you know, kilobar pressures and very high salinities in the fluids, that when these fluids, if they reach anywhere near the surface, they phase separate, right? And you just get it with steam and intense alteration of the rocks around them. The targets that we're looking at are basically standard conventional fluids, but they're at 400 degrees, which is what they have in Iceland. They have basically geothermal systems that are above 400 degrees. We're not targeting 500 degrees, 600 degrees. Those are more interesting experimentally, research wise, but our real target is sort of 375 to 500, right? And 150 to 300 bars. And those aren't magmatic fluids. Those will be very dilute, high temperature, high enthalpy fluids. So yeah, we often get this thing of mixing up magmatic fluids with supercritical conventional fluids, typical fluids. If you go to the Philippines or Indonesia, you're looking at magmatic systems. You're actually drilling on the sides of volcanoes. Then you're starting getting acidity coming in from magmatic volatiles. And it's not necessarily the water, it's just the volatiles that are getting into your system and causing the systems to be very acidic.
Okay, so they're not necessarily the same thing, but they could be, right?
Well, if you get a fluid that's 400 degrees, but it's partly magmatic, in fingerprint is magmatic. If you have enough volume and flow, then you have a heat source. The problem is developing a really high salinity, low pH fluid is going to be extremely difficult, right? And you're going to need very, very expensive materials. And well, I mean, no one's done it yet. So, except maybe some places they do it, but they do caustic dosing, and of course, it's going to be very expensive then.
Yeah, and caustic dosing has not exactly been very effective or very consistent in a lot of these demonstration
NaOH
projects.
is expensive. NaOH is expensive.
Yeah. Okay, so let's get to a few more questions from the audience. Something basic. Which software do you use for modeling?
Geochemist Workbench, version 2023. I just finished a short course 4 nights in a row at 1 a.m. to 4:30 a.m. Last session was last night. I've been using GWB for 20 years. I teach a course in GWB, but I attended their short course because I want to learn about new capabilities. So yes, I swear by it. If you don't have it, buy it. No royalties here.
Okay, another question from the audience. Did you test different injection rates for CO2 injection? And has there been any difference in the results?
Very good question. I didn't want to. I already went 36 minutes. I didn't want to go any. Didn't. I already had too many slides probably. We have done it at different CO2 concentrations, and what's very interesting, and this is something that we're working on as a capability, is looking at no CO2 and then intermediate CO2 and then high CO2, and then what we do is we take those 3 experiments and we calibrate a tough react model that actually takes the silica scaling rate from the experiment and the CO2s, and then it can predict the actual silica scaling rate at various temperatures and CO2 concentrations, and it gives you exactly that sweet spot where the CO2 is just right for mitigating, 95% of the scale or whatever. So yeah, that's a good question. We have tried it. These experiments are extremely long. They're 4 weeks long, so you don't want to be testing like 20 different CO2 concentrations. So the solution we've come up with is by using experimental data to calibrate a numerical model. And then we can predict the CO2 scaling at various CO2 concentrations and temperatures.
Okay then, some more questions on tracer testing. What have I mean? Can you tell us a little bit about what have you observed on behavior of tracers in supercritical fluids in these conditions?
Okay, so that's a very good question as well. One of the problems that's going to come up in the future is what do we use as a tracer for systems that are above 375? Uh, we have tested NDS, as you probably know. They don't work above 350 is probably the limit for 2NSA. Anything higher and you're asking for trouble. We have done all the NDS at 400, and even in the experiment, like a residence time of 2 hours, they're gone. There's nothing left. But they produce naphthalene as a breakdown product. And so one of the things that we're testing now is the stability of naphthalene and 1-naphthol, which is the alcohol of naphthalene. We're looking at the stability of those compounds at higher temperatures. And the interesting thing about naphthalene is it's volatile. So it's not a dissolve. It doesn't like to be in water. So it actually is a volatile species. So it will partition into a low density fluid. So Lucek is actually, Lucien Salkowski is actually testing it as part of a research program to see if naphthalene is a useful tracer, say below 450. Anything above that, probably any organic is not going to be stable. I wouldn't think. I could be wrong. They find organic molecules in volcanic fumaroles. They're quite often they find them in. But on the other hand, there is one thing that does work, and I can guarantee you it will work, and that's iodine 125. So radioactive iodine, it doesn't care about temperature or pressure. It will be stable at 800 degrees. It's a very effective tracer. You can detect it for about a year and a half after you inject it. However, it's radioactive. So it attracts a lot of health and safety and logistical things, and it's very expensive to do an iodine tracer study. But it works. It's very, very, I've done myself personally a couple of these tests, and you're still detecting it 18 months after it's been injected, which you could never do with the NDS.
Okay, that's excellent insight on tracers. Okay, we have 1 minute left, so we just one last question to wrap this up. Maybe something of a summary. So, based on whatever studies you've done so far, and also your experience in geothermal, what would you say are the major challenges of trying to utilize supercritical geothermal resources in terms of, say, scaling or corrosion or just the difficulties in material selection?
Material selection is just a matter of finding the most resistant material. The problem is the cost. And you can line your pipes with platinum. It'll be very, very expensive, but it'll be very resistant as well. I don't think material selection is the problem. It's the cost of the materials that's the problem. So I think corrosion will be an issue. Scaling, not sure. It really depends on the sort of chemistry of the system, right? I mean, if you're using a heat exchanger, then you might not have any problems because you're doing the heat exchanging underground somewhere, right? And it's just mining heat basically. But if you're bringing that fluid up to the surface and condensing it or putting it through a heat exchanger on the surface where you've got surfaces of metal and plant surfaces exposed, then you may have to be more worried about particularly acidity, I'd say, and not so much dissolved material. I don't know if silica would be a problem. I think it's going to be acidity that's going to be the problem because it's going to be quite acidic, I think. So again, material selection and corrosion may be the most difficult thing to deal with.
Has there been any inquiry on, say, the resistance of electronics, or the stuff they used for drilling in supercritical conditions?
Can't answer that question. Not my department. Not my pay grade. You'd have to ask a drilling engineer, someone in Iceland. That obviously you need special materials, special drilling techniques to deal with such high temperatures.
Okay then, and on that note, I think we are a little over the time. So thank you, Bruce. That was very good. That was a very interesting presentation also, and I think that for any geothermal companies out there that are interested in your services, you are open to to a more commercial approach to
Yes.
this, right? Okay.
Yeah, we've been doing contracted simulations for about 15 years now. So we've done many reinjection simulations from plants all over the world. We've done many corrosion tests, looking at ultra, extreme conditions where most labs don't have the capability. And we just in the last we'd say 3 years started doing CO2 reinjection simulations to look at effects on the reservoir. So that's the latest. We're doing the silica polymerization benchtop. That's all just contracted commercial work because we don't have any research project looking at silica polymerization at the moment. So yes, I'm open to any inquiries at all.
Okay then, and I anticipate there will be interest. As you said, do you have equipment, or you can simulate conditions that don't really exist anywhere in the world, or equipment that doesn't exist anywhere else, right?
So I'll leave a takeaway message for everyone that's listening. What I do with a client is I sit down with them and say, what question do you want answered? And then we design the experimental apparatus and protocols to test that question or answer that question. So if you want to test something, all you do is just send an email and say, are you able to do this? And I can say, yes, we can do it, or no, we can't. And if we don't do it already, which you've seen what we can do, then we'll sit down with the team, Peter, Lucek, and myself, and Dave, and we will say, okay, can we do this with the equipment we have? And how would we do it? So that answers your question. Just ask me, can you do this?
Okay then, and on that note, just get in touch with Bruce. Anyone who's in the audience right now, or anyone who's listening to this recording, just get in touch with Bruce if you have any questions. Thank you, Bruce. Thank you for
All
that.
right. No problem. Thank you. Thank you, everyone else.
Thank you. Thank you, everyone, for coming. Thank you for your time, and have a happy weekend.
All right.